Our first lesson is going to be on properties of rational exponents and radicals. A lot of these properties we've already seen before. We did them in Algebra 1. So the product of powers is when you are multiplying two things with the same base, we would add together their exponents. For power of a power, that's when you have something that already has an exponent being raised to another exponent, we would multiply those powers. For power of a product, as long as it's product, multiplication inside, not addition or subtraction, I can distribute the power. So it would go to both. So that's a to the m and b to the m. Oftentimes these two properties are put together. So we just have to make sure we're multiplying. If a had an exponent here, I would have multiplied that by m, and b also would have gotten its exponent multiplied by m. Negative exponents, as you recall, we're not allowed to have in our final answer. So anytime we have a negative exponent, we're going to want to move it to the opposite side of our fraction. So in this case, it would go to the denominator. Zero exponent, anything to the 0 power is equal to 1. Quotient of powers, quotient means division, right? So if I have the same variable or number and they have powers on top and the bottom, I would subtract them. A lot of times when I look at this, I'll look at which side had the bigger power, and I'll just make sure I keep my answer there. So if n happened to be bigger, I would do n minus m, and I'd make sure my answer went into the denominator. Power of a quotient is a lot like power of a product. I'm going to distribute the power to both the numerator and the denominator. So this will work for all of our regular exponents and for our new rational exponents, our fractional exponents. So here's our first example. We have 13 being raised to the 1/3 power and 13 being raised to the 1/6 power. So I know I'm going to end up doing 13 to the 1/3 plus 1/6. All right, we're going to add those powers. But if I have two fractions with different denominators, I need them to have the same denominator first. So I'm going to turn this 1/3 into 3/6. So now we have 13 to the 3/6. Oh, sorry, 2/6. I'm lying already. 2/6 plus 1/6. That becomes 3/6. Sorry about my writing, guys. And 3/6 we know is 1/2. So our final answer would be 13 to the 1/2. All right, and that's our answer. For B, I have two different terms inside, each with an exponent and an exponent on the outside. So we're going to distribute this exponent to both of our original parts. So we're going to have 1/5 times 5, and 1/5 times 5 is really just 1. So this becomes 5 to the first power, or just 5. And we're going to multiply that by 8 to the, and when I raise 1/4 to the 5th power, that's just going to become 5/4. And that's it. There's nothing else I could do there. That's my answer. For C, there's two ways I could really go about this. Anytime I do have two different numbers, but they have the same power, I could multiply them first if I want. In this case, it's not going to make a difference, so I'm going to focus first on distributing the power. 3 times negative 1/3 is going to be negative 1, so I have 12 to the negative 1 times, and I'm going to distribute there too, 9 to the negative 1. And if you recall, we're not allowed to have negatives, so this is going to become 1 over 12 to the positive 1, or just 12, times 9 to the positive 1, or just 9. And now it's really obvious to see that we will get to multiply these, and we get 1 over 108. All right, and that would be our final answer. For D, we have a quotient. We're dividing. 8 to the first power is really like 8 to the 9 over 9th power, right? 9 over 9 is really 1. So I'm going to subtract these. 9/9 minus 1/9. And we're going to get 8/9. So this is really 8 to the 8/9. And that's our final answer for that one. Now for E, I could distribute to both, but I have both numbers with the same basically radical, right? This is really the fourth root of 56 and the fourth root of 8. And if I have two numbers with the same root, I'm allowed to divide them. So I'm going to divide 56 by 8 first, and I get 7. So what I really have here is 7 to the 1/4 raised to the third power. And this becomes a lot simpler because now all I have to do is 3 times 1/4, and my answer would be 7 to the 3/4. All right, so what I'm going to have you do is you're going to pause the video and try these, and then once you're ready and done, unpause, and I'll give you the answer. All right, if you've unpaused, we have 2 to the 5/4, we have 3 to the 3/4, we have 4 to the 3/2, and we have 5 times 7 to the 3/4. All right, if at any point you have any questions on these lessons, just send me an email and I can help you out. All right, our next thing is the properties of radicals. So we have seen this before when we had regular square roots. It applies to any radical beyond the square root, so the cube root, fourth root, and so on. So if I have the product of two numbers under the same radical, I could separate it. If I have the division of two numbers under the same radical, I could separate it as well. And vice versa. If I started with two separate ones, I can combine them into one. If I started with two separate, I can combine them into one. In this example, we have 4, the cube root of 4, and the cube root of 128. So since they're both the same root, I'm going to multiply them. I'm going to get the cube root of, and I'm going to do 4 times 128. And when I do that, I get 512. Now, if you look at that green sheet we had with all the different popular cube roots and so on, 512 was on that list, right? 512 is really 8 to the third power, so this simplifies to just become 8. In B, we're going to do the same thing. We have division, so we'll divide. So now my answer will be the fifth root of whatever 192 divided by 6 is. That's 32. And again, if we use our handy dandy sheet, the fifth root of 32 is 2. Okay? Same deal. You're going to try these, pause, and when you're ready, unpause to see the answers. All right, if you've unpaused, this one is 3, and this one is 5. All right, next, we're going to talk about reducing radicals. So this is a lot like reducing our square roots. So if you remember, if we had something like this, the square root of 50, we were looking for a perfect square that went into 50. So we could look at that as really being 25 times 2. And when I took the square root of the 25, it came outside, and the 2 stayed in. You also might recall that we looked at it as a tree. So we took 50, and we broke it down to maybe 10 times 5. 10 can be broken down further to 2 times 5. Right? Both of those are primes, and 5 was a prime. And for square roots, anytime you had a partner, they got to go out together as 5, and whoever didn't have a partner stayed in. So we can do this with any kind of radical, and it's considered completely reduced when there are no perfect nth power factors left. There are no fractions inside the radical, and there are no radicals in the denominator. So we're going to also have to rationalize our denominators. If you have a hard time coming up with the perfect nth power number inside, you could always do the tray, and whatever root it is the number of matches you have to have before they come out. I'm going to do it as finding the perfect power. So we look at our first one, the cube root of 500. If I look at my list of perfect cubes, 125 is a perfect cube, and 125 goes into 500. So I'm going to rewrite this as the cube root of 125 times 4, and the cube root of 125 is 5, and I can't take the cube root of 4, so that's going to stay. And that would be our completely simplified answer. There's no fractions, there's no denominator, and this cannot be taken, right? There's nothing that goes into 4 that's also cube root besides 1. B, same idea. I'm going to look at my list of perfect fifths. 243 is a perfect fifth, and 243 times 2 gives me 486. So I'm going to turn this into 243 times 2. I'm able to take the fifth root of 243 and get 3, and then I'm left with the fifth root of 2. So that is completely reduced there. Now, C and D become much more complicated. Nothing is going to go into either 20 or 9 that is a perfect cube. But 9, I know, is really 3 times 3. So this is the cube root of 20 over the cube root of 3 times 3. If I want the denominator to go away, I need to have 3 of whatever number I have in here. I have 2 so far, so I need 1 more. So I'm going to multiply this by the cube root of 3. So now I have 1, 2, 3 on the bottom. And whatever I do to the bottom, I have to do to the top. So the top becomes the cube root of 60, right? 20 times 3 is 60. And on the bottom, I really have the cube root of 27. And we know the cube root of 27 is just 3. So this is completely simplified. All right, that is a trickier one, rationalizing these denominators. I'm not really going to make you do that much further than beyond this lesson. All right, in D, I have the fourth root of 19 over the fourth root of 4. 19 and 4 do not reduce. I can't go that method. So I'm going to rewrite this as 4 is really 2 times 2. Right? We always want to find something times itself to give us that number. So we have the fourth root of 2 times 2. So now I really need 4 2's altogether. So I already have 2 of them, so I need 2 more. So we're going to multiply both the top and bottom by the fourth root of 2 times 2, or 4. Oops. So the top is really going to be 19 times 4. And when we do 19 times 4, we get 76. So we have the fourth root of 76 on top. And this bottom was really 4 times 4 is 16, the fourth root of 16, which is just the number 2. So that is completely simplified there. So you guys are going to try the next ones. Again, pause when you're trying them and redo it when you are done and look to see the answer. All right, if you've unpaused, our answer here was 2 cube root of 13. And for number 8, we would have the fifth root of 24 over 2. That is completely simplified. Looking at the next examples, now we want to write the expression in simplest form. And we've kind of done something like this before when we had to find the conjugate. And we did this really with complex numbers, but we also did it with some radicals. If I want to get rid of the radical in the denominator here, I'm going to multiply by the conjugate on the top and the bottom. And if you recall, the conjugate is always the same two numbers, right? The root 7 and the 2. But we're going to change the sign. So it was originally a negative. Now we're going to have plus. All right, so in the first one, 1 times that is just going to give me root 7 plus 2 on the top. The bottom, though, we're actually going to distribute. So I'm going to do root 7 times root 7, which is root 49, or 7. Root 7 times 2 is plus 2 root 7. Negative 2 times root 7 is minus 2 root 7. And negative 2 times 2 is minus 4. So the lovely thing is those cancel. And I'm just left with 7 minus 4. So we get root 7 plus 2 in the numerator over 3. Okay? Let's try B. So in B, our conjugate is going to be 5 minus radical 3. So we're going to multiply the top and bottom by that. And I could distribute right away here if I want, but I'm actually going to keep it like this for a second. You'll see why later. So we're going to have 2 times 5 minus radical 3. And on the bottom, notice we're always going to cancel those middle two. So all I really have to focus on is the 5 times 5, right? We're going to get negative 5 root 3 plus 5 root 3. Those cancel. And then negative root 9 or 3. This turns into then 2 times 5 minus root 3 over 22. Now remember, anything on the top and bottom with multiplication can be canceled. So 2 over 22 is really 1 over 11. So my final answer here would be 5 minus the square root of 3 over 11. Right? That is completely simplified. Try the next one. You're going to pause and restart when you are ready. All right, if you've unpaused, I have 18 plus 3 radical 2 over 34. Okay, if you hadn't simplified, you would have originally had 3 times 6 plus radical 2. All right, make sure you do distribute that to get the 18 plus 3 radical 2. All right, the next thing we're going to talk about is radical expressions with the same index and radicand are like radicals, all right, almost like variables. So to add or subtract like radicals, we're going to treat those parts as if they were variables and only focus on the coefficients, all right, the numbers in front. So if I look at this, I have the 6 through to 17 here. I have the 6 through to 17 here. This has a coefficient of 9, and even though we don't see it, this has a coefficient of 1. So I'm going to focus on the 1 plus 9 to get 10. And then I'm going to bring it down as if it was a variable, the 6th root of 17. Okay? Same thing here. They might not be written as radicals. They're written with their exponents. But this is really the cube root of 7 and the cube root of 7. So I'm going to focus just on the 5 minus 8 for negative 3. And then it's 7 to the 1/3, or the cube root of 7. And that's it. That's all I have to do for that. C and D become a little more complicated because they're not simplified. They're not like radicals right now. But the good thing is, because I know this is a 3, my goal should be to get this to be a 3. So I'm going to look at what is 48 divided by 3. And 48 divided by 3 is really 16. So I'm going to rewrite this as 16 times 3 in here. We're keeping the second part the same. And this goes back to when we were reducing the radicals before. The 4th root of 16 is really 2. So this can be rewritten as 2 times the 4th root of 3. And now this is minus, we're going to call it 1 times the 4th root of 3. And focusing on the 2 and the negative 1, 2 minus 1 is 1. So it's 1 times the 4th root of 3, or just the 4th root of 3. D, same idea. I have a 9 here, so my goal would to be get this as a 9, right? 9 cannot be reduced there. So 72 is really 8 times 9. Okay, I'll rewrite the rest. The cube root of 8 is 2. So now on the outside here, I have 5 times 2, and then the cube root of 9, plus 4 times the cube root of 9. So this is 10 cube root of 9, plus 4 cube root of 9. giving me a total of 14 cube root of 9. All right, and that's completely simplified. Again, try the next set, pause it, and when you're ready, unpause. All right, for 10, we get 6 times the fifth root of 12. For 11, we get 12 times 9 to the 2/3. And for number 12, we get 3 times the cube root of 5. All right. From here on out, these are a little bit more advanced, and we may or may not have you be required to know these, but I am going to show them to you because you never know when you're going to see them. So we can have variables inside our radicals, the same way we could have numbers inside our radicals. The number part we treat the same. The cube root of 27 is 3, so that's nice. When it comes to radicals, though, I'm really looking at how many times does the index go into the power. So I'm looking at d to the 12th, so 12 divided by 3. If it goes in evenly, that's fantastic. So 12 over 3 is 4, so I get d to the 4th power, and since there was no remainder, there's nothing left inside the radical. All right, it's not going to be the case later. Here, the 4th root of x to the 4th over y to the 16th, so we're going to make sure we take the 4th root of x to the 4th. 4 divided by 4 is 1, so it's just x, or x to the 1st power. 16 divided by 4 is 4, so we get y to the 4th, and both of those went in evenly, so there's nothing left inside. Now when we get to this one, it doesn't work quite as well. So there is no cube root of 2, so that's going to stay inside. When I try to do 13 divided by 3, it does not go in evenly. So 13 over 3 is really 4 with a remainder of 1, which means I'm going to take an a to the 4th out, but there's still going to be an a to the 1st left inside. 3 over 3 goes in evenly, so we're going to be able to do that nicely. And then 8 over 3 does not work as well, right? When I look at 8 over 3, 3 goes into 8 twice with a remainder of 2. So we will be able to take out a c squared, but there's also going to still be a c squared inside. So now let's work on this. We knew that left inside was the 2, a remainder of 1 on the a, so we have an a there, and the b came out totally, and the c had a remainder of 2, so that's inside. We know we were able to take out a to the 4th. We were able to take out 3 over 3 is 1, b to the 1st, and we were able to take out c squared. So this would be my final simplified answer. Right? I know it's complicated. D gets even worse because this does not work nicely, right? We could start by doing that. 13 over 3, we know goes in 4 times with a remainder of 1. So we're going to have x squared unchanged over, we could take out y to the 4th, but then we keep the cube root of y to the 1st. And if you're cold, we're not allowed to have radicals in our denominator, so here I would have to rationalize, and I'm going to multiply by, I want to have total of 3 y's, I only have 1 here, so I'm going to multiply it by 2 of them, right, on the top and the bottom. So now on the top, I'm going to extend this a bit, I get x squared times the cube root of y squared. On the bottom, I still had that y to the 4th, but now I have the cube root of y to the 3rd, which is just y. So now I can still combine those, x squared times the cube root of y squared over y to the fifth. Okay, and that's my final answer there. All right, the last one here is more like our old exponent stuff. So regular numbers get to be treated normally. 16 over 8 is 2. Then I have an x on the top and an x on the bottom. So this is x to the 1, or 3/3. All right, try to get it in there real tiny. Over x to the 2/3. So the top has more. And if I do 3/3 minus 2/3, I get 1/3. So I get x to the 1/3. I only have a y in the numerator, so I'm just going to get to rewrite that. Y to the 1/3. And then the z has a -4, and we know anytime there's a negative, it should move to the opposite location. So I'm going to move z up to the +4. And that's all I have to do for that one. Almost done. So these, pause, try them, and then look at your responses. So if you're unpausing, we should get 3q to the third. For 14, I should get x squared over y. And for 15, I should get 2x to the 1/2, y to the 1/4. All right, almost done. So some of these are going to be a little easier as long as they're exactly the same. We're going to still treat them as variables just like we did before. So cube root of x are good. We're going to focus on 6 plus 2, 8 cube root of x. For b, these are not the same. So I'm going to focus on one part at a time. So for this side, the 16 fourth root of, now this is 3. And if it helps you to do it like this, p to the 6th is really p to the 4th times p squared minus p, and then the 4th root of 48. I know I'm looking for a 3, is really 16 times 3. And then we have p squared. So on this side, 4 over 4 goes in nicely. So this is going to be a p coming out, p to the 1st. And I'm left now with fourth root, of p squared. Oh, 3p squared. Here, the 4th root of 16 is 2. So I can take out 2, and I still have p there. And I'm left with, right, that's gone now, the 4th root of 3p squared. And now these do match, right? 4th root of 3p squared, 4th root of 3p squared. So I'm going to focus on the 16p minus 2p. And we get 14p times the 4th root of 3p squared. All right, these are your last one to try. When you pause it, when you're done, check your answer. And again, if you have any questions, just send me an email. If you've unpaused, we should have 2w squared times the square root of w. All right, have a great day.